All right, so welcome to the Majastra Day. Thanks very much for the great introduction. My name's Stephen Chin. I'm the Java Community Manager for Oracle. So I do the Java Twitter handle, social media, our community platform site. And I've come to Chennai a bunch of times speaking at different user group events, and I'm here this week for Cloud World Developer Mumbai, which is this coming Friday over on the other coast. But what I'm going to talk to you guys today a little bit about is Raspberry Pi, Java SE embedded, a little bit of JavaFX running on it, and some performance tuning. Sound good? And I have a demo as well, sitting in front of you, a little toy to show off. So this is first a little bit about Java communities. So there's worldwide about 314 plus user groups. So you guys are all user group members supporting the community. Thank you. There's 9 million Java developers worldwide. So there's a huge development community of Java folks. And there's 150 Java champions. So the Java Champion program is a way you can get more involved. So I'll chat more about this in the second presentation. And over 50 user groups. So all this stuff is, a lot of work managing the Java community. But I think it's even more work to do video game emulation. So we're gonna talk about how you can emulate the NES console. We'll see if the volume works or not. Oh, I know, the volume's probably going out to that box. Oh well. So has anyone played the Nintendo as kids growing up? What did you guys have the Super Famicom? Maybe Sega? More Sega in India? Okay. But some video games, right? So the NES was quite a popular console. It sold 61 million units worldwide. In the US, we got these white consoles, Europe as well. In India, it was called the Super Famicom, and they had a red version of this. And there were over 826 different games. Kind of the NES revitalized the video game industry at the time, which was suffering after Atari wasn't doing as well. It has a simple Motorola chip. It's a variant of the 68000 series, 3510 transistors. They disabled some features, and Ricoh's the one who's actually manufactured the chip for Nintendo. And there's 92 million synchronization points. So one of the challenges with doing video game emulation is to get the precise behavior of these old chips with the timings. So there was a CPU, there was a graphics processing unit, a GPU, or a pixel processing unit. They call it a PPU. And there was an audio processing unit, an APU. And these three chips had different timings. And so the game manufacturers would play tricks with to implement features in their games, like side-scrolling or different backgrounds. They would hack the hardware, and they would do things in the middle of scan lines. So they could do like side-by-side split scrolling and have special effects in the background, which weren't part of the original hardware, but they were taking advantage of writing to registers from different chips and doing little hacks. So as a result, you have to be extremely precise to emulate games accurately. Otherwise, you have artifacts which show up in the games because you're not precisely emulating the chip. So it's quite a hard challenge, and the hardest part of this, of course, is playing all of these video games. So this is one of the hardest games. Anyone know this one? No, this is Ninja Gaiden. But it's one of the top 5 hardest games of all time because it's you get no lives. Well, every time you want to continue, you have to. If you power off the console, you start from the beginning of the game. So there's no memory state. And most of these enemies, like you would you wouldn't die from the enemies, but you die from falling in pits constantly. So a lot of the stages were very poor level design, extremely difficult. Enemies would respawn constantly. And the boss was extremely difficult to kill. Like the end boss. I think it takes you about as long to beat the end boss as the rest of the game. And then when you kill him, he dies and he comes back. And then he's bigger and he's more difficult to beat. And then you spend another few days on that. Then you kill him and then he dies and he comes back a third time. So actually beating the game, I finally beat it when I was a kid, but it was like 2 weeks of leaving the console on. So extremely challenging. This one looks cute. You guys know this name? Guys, this is Mega Man. It looks cute, but it's also the Mega Man 1, the original version, is one of the hardest games again because it was extremely the mechanics for it were extremely difficult to control your character. Anyone do flying games? Yeah. So this is Gradius. This is actually a Super Nintendo game, but in general, flying games required a lot of precision to make sure you were dodging and hitting stuff. And then once you play enough games, you reach nirvana for video games. Anyone know what this code is? What? Well, guess what it does. Yes, very good. So for Konami, this is the unlimited life code. So you get like some games you just like Contra you couldn't beat until you cheated. It was almost impossible to beat the games without getting more lives. All right, so since you guessed right, I'm going to challenge you to a video game competition. All right, so we got a little console here for you. So we're going to play Super Mario Brothers. Yeah, just hit start. Yeah. So you're going to play on that screen, and I'm going to play in my IDE. So you get a physical console. I have to actually play with a funky keyboard here. So this is a HalfNes project. And it's the same code that's running there, but that's the Raspberry Pi ARM version of it. And these are actually all games I own. So I asked my parents to ship me my. All right, you're started. You're trying to get a head start on me. Okay, so count down to 3, 2, 1, go, and then we'll play. All right, you ready? Yeah, go.
3, 2, 1, go.
All right. Oh. Anyone know that 1-up secret? So you guys have probably played Mario before, right? I think this is even if you haven't played Nintendo, I think there's enough Mario stuff out there that you can't avoid it. So how you doing? You almost at the end? Yeah, it's gonna get close. Oh, you got the firepower. No fair. All right, how you doing? Almost. See, this is my hard work of practicing for instead of coding, of practicing playing video games for months. Done. All right, give him a round of applause. All right, so I should have mentioned this earlier. So I have some. Oops, I died now. I have some giveaways as well. So you'll get the first one. So these are the stickers for the Night Hacking live broadcast site. So we're live streaming now. So the whole presentation of what we're doing that delayed? Oh, that's still playing. Okay. Pass it around so people can try it. Yeah, pass it around the room. Yeah, not right now. People can try. Yeah, so we're doing live streaming right now on the Night Hacking website. So thanks very much for setting up the internet to make this possible here. I just also recently did a crazy Germany tour. So I was traveling around Germany and speaking at JavaLand and a whole bunch of different conferences over there. So, subscribe to the YouTube channel, the Night Hacking YouTube channel and Ustream channel. And then, watch some of the interviews or broadcasts on the site. But since you guys have been on the stream, we're going to be recording all day today, then the criteria for getting one of these is you have to be on the stream. So I'll leave these in the front, and you guys can grab one for yourself, not for your friends. They have to come. They have to come to the Madras Jug meeting if they want to get one. Okay, so this is the device which you were using to play. It's a 3D printed gaming console, and it runs a Java-based emulator for doing the game emulation, and it has a Raspberry Pi and other embedded hardware inside of it. So we're going to talk about the hardware first, I think. Yeah, I think hardware, then software, then 3D printing. So hopefully, one of these topics is interesting to you guys. So first, a little bit about the hardware inside of it. So who has a Raspberry Pi? Okay, very good. Who has the what's the price of Raspberry Pis in 3,000? All right. Who and 60 3,000? Yeah. Okay. Who has $50? Hopefully. Okay. So yeah. So you can probably you should probably take that $50 and turn it into a Raspberry Pi. So it's a fun embedded computer. It's a full computer. You can hook it up to a display, a keyboard. It runs a full Linux distribution, so you can actually do programming and do real stuff on it. What makes it different from a general purpose computer is it has these extra GPIO pins on the side. And this lets you hook it up to hardware and electronics. So like the buttons inside the game. Pass the game around. The buttons inside the game are, and don't turn off the game. So just let it run. If you want to switch games, press start and select at the same time. And then you can switch games. So the main thing that distinguishes the GPIO headers and the buttons in the console are hooked up via GPIO pins. You can also hook up like accelerometers, temperature sensors. You can hook up, buttons and switches and all sorts of electronic things. So it's a really nice platform for building small embedded hardware, and it runs on very low power. You can power it over micro USB, about less than 1 amp. Sometimes down to 300 to 500 milliamps. And you can power it off battery as well, so that device is running off a little battery inside of it. So it's a good platform for prototyping. Does anybody want to guess what these two headers are for on the top? Do you guys know?
What is the camera?
Yep, camera, good.
It's for the display.
Yeah, other ones for display. So camera and display. And okay, so this display port, I think it's this one here. It's used to hook up to an LCD screen. And unlike the HDMI, which is used for displays or TVs or large electronics, this one powers the display, and it also has touch support, and it doesn't require conversion. Normally, when you convert, like when you have an HDMI screen, it has a electronics board which takes the HDMI signal and converts that into an LCD signal. And actually, that's a good question because for a portable display, there is only one display which currently works with that display port. It's the Raspberry Pi Foundation 7-inch display, and it's big. Well, for a small gaming platform like this, it's large, and it's also heavy. they have a big piece of steel on the back, and it requires an extra daughter board, so it's slightly over-designed. So it wouldn't fit in a case like this. Is it still working? Yeah. Okay. So to have a portable display, you need a different option for a device like this to hook it up. And there's a bunch of different types of displays you can hook up. So you mentioned HDMI. HDMI is what I would recommend if you're hooking up your Raspberry Pi at home, right? You can hook it up to a TV or a monitor. It's quite easy to do. One disadvantage is in a small device like this, you need a board to convert from HDMI back to an LCD screen, and you need to power the board and the screen. So it's difficult to do that in a small embedded device. It's not ideal. There's also a composite port. This is the older interface, like, you know, back when we had CRT tubes. And it's not only requires a back converter board, but it's also low quality. So it, you know, it's not that great of a video signal. SPI is another option. So the SPI bus is a special high-speed serial bus on the Raspberry Pi. The problem is it's high speed for serial, but it's relatively slow for graphics. You get about 10 to 15 frames per second from the SPI bus. So you will see some displays they sell online, like Adafruit sells some displays which go on the GPIO pins, and they use SPI with some special drivers, but the resolution, the refresh rate of the screens is not really that good. The Nintendo emulator requires 60 frames per second because the original Nintendo system was on NTSC or PAL, and it was an interlaced display where it was writing every other line. So to accurately emulate it, you need a screen which can support 60 frames per second. Device tree support is the last one, and this is a hack, but it works quite well. Basically, you convert the GPIO pins to be used as LCD pins instead by adding in a new device tree file to the Raspberry Pi's boot sector. So Adafruit sells an adapter board like this, and it hooks up to the GPIO pins. It has an LCD out. It maps the GPIO pins to the LCD pins. And because it's a direct LCD connection, there's not a conversion happening to like a composite or HDMI signal. You get the advantage of all the speed of a native LCD display, low power usage. So this board will also power your LCD display at the same time. And it also supports touch. So there's a USB touch support. The challenge with this is that because it's using most of your GPIO pins for the display now, you only get left with 6 GPIO pins and none of the interesting ones. So you don't have UART, which is serial. You don't have I2C. I mentioned SPI bus, which is the high-speed serial peripheral interface. That also is not available. So basically, you don't have any interesting pins. You just have 6 on-off basic pins, which is challenging. So to implement an NES controller, how many pins do we need? 8. Very good. So if we count 1, 2, 3, 4, 5, 6, 7, 8. So not very good. We want more pins. So anybody play Mario? Yeah. So my daughter played Mario for the first time on this console when I had her testing it, because she's played the later Marios, not the original. And when she got this message, she was not happy, because in a modern video game, when you beat a level, this is the end of the first level. There's supposed to be like fireworks and like dancing and applause, right? Positive reinforcement, not this. So this is kind of how I felt when I realized I was short 2 GPIO pins for the design of this, because I need 8 and I have 6, and it's not very rewarding. Does anyone have any ideas how you could work around this limitation? Multiplexing. Oh, you know something about keyboards. So what's here, I'm going to give you the mic so you can explain this. What's multiplexing?
So, say for example, we are using a 2-pin to convert it to 4 kind of signals. So you can make it something like you have 3 pins. Say, for example, 2 for signal and 1 for applying the input to the out. You have to convert that input to output. So you are switching. You are going to multiplex from 2 to 4 actually. So you are going to send signal like 0 or 1 in the signal pins, and you are going to control the values coming into the serial port. So you get something like 4 output from the 4 output pins. So that's that's something that you could remember.
Yeah.
Not
Yeah.
beyond that.
All right. Very good. So it's possible that you could implement something like that. The challenge is you need some sort of controller to do that effectively, right? So I'd have to have an extra board inside the Raspberry Pi, which was doing the multiplexing, and I'd have to have some sort of protocol so that when you're pressing and releasing keys, it's sending the right signals. Another really common solution for this is matrices. So that's what your keyboard uses in your laptop. And a keyboard, the way a keyboard matrix works is it has a set of rows and a set of columns. And whenever you press a key, the key exists in the matrix somewhere between the rows and the columns, and it's constantly sending signals on the columns, and then it's checking the rows to see which rows are active. And between the combination of rows and columns, when you press a key, you can figure out uniquely which key you press by sending signals on the columns and checking the rows. But I didn't do either of those because keyboard matrices too require more hardware, and then you have to do polling. So what I did instead was a little hack. I used a couple diodes, and I wired together the left and the right button to the start, and then up down to select. So the way this works is you can't actually press left and right at the same time, right? So normally if you wired them together, it wouldn't work. But if you put diodes in the middle for current protection, then this prevents the current from flowing the wrong direction. And now when you press left, it'll work. When you press right, it'll work. When you press start, it sends a signal to left and right, like you're pressing both simultaneously. So this works great, except in one case. Can anyone think of the failure case where this doesn't actually work? Yeah, okay. So if you press start and left, for example, at the same time, that would register as start. Same thing, like if you press select and up, it would register as select, not up. So fortunately, most games don't require that you jam start and up or select and up at the same time, right? It's an uncommon gesture. Except my buddy who did the emulator pointed out that there's one game, Mike Tyson's Punch-Out, where for the smash moves, you have to press, I think, select or start and an arrow key at the same time. So I broke one game. But I think it's a reasonable trade-off. It works most of the time. And you can see it works quite well for 99% of the games. This is the wiring for the RetroPi, so you can see it's plugged up to the Kippah board. It's a little bit messy in the diagram here because the idea here was this breadboard I'm going to remove inside the case. So there's no breadboard inside the case. It's just wired up directly to each other. This is the button layout on the breadboard. So there's a little directional arrow, a couple buttons for select and start, and then ones for the A and B keys. This is some soldering to the Kippah. If you were doing this yourself, I would recommend using twisted core wire, not solid core. It's a little bit easier to use the twisted wire when you're wiring multiple wires to the same contact point like this. And then this shows the wires connected. Again, like if you're doing this yourself, this picture doesn't show this, but in the final version, I have heat shrink wrap over these so the connections don't cross. And check it with a multimeter so you're making sure your connections don't touch. But it's not too hard to do by yourself. This is all quite possible. And this is the completed gaming console showing the working game. So something, you guys could try and do yourself. And all of the hardware here you can purchase from Adafruit, which is an online. You guys know about Adafruit? Okay. So they sell small electronics stuff. And all of the parts here, like the directional arrow and the buttons and everything, are available from them. The only ones which aren't is I use a slightly different A and B button. So if you're going to do the 3D printed case, you need to get those specific buttons. If you're not going to do the 3D printed case, it doesn't matter. Okay, so next I'm going to talk about the software that goes inside of this. So I mentioned it's a, well, before I do this, does anyone have any questions about the hardware? No? Can you buy from Adafruit in India? No? Okay. Okay, I know they ship to Europe, but I guess not India yet. Okay. The Raspberry Pi is just the board inside of it. This is my custom design, so.
We have 3 boards inside here. One for your custom joystick. The other one is for the adapter for the display.
Yeah, so this is the Raspberry Pi, right? The green one. The blue one is the Kippah. And yeah, there's no breadboard inside. Yeah, there's also no PCB inside. I'll show you what it looks like, but it's all 3D printed. So just these 2 boards, and then it all layers in nicely. And this is the LCD screen. So if you want to try this project at home with your own Raspberry Pi, you can do the breadboard easily. That's easy and cheap. The Raspberry Pi is easy. And I would just hook your Raspberry Pi up to a TV or screen rather than doing the LCD and the Kippah if you're not going to 3D print the case. Okay, so let's talk a little bit about the software inside of this. So the emulator I'm using is called HalfNes. It's a project written by Andrew Hoffman. He works for University of California. And this is one of his, part-time projects. He's been writing this emulator on the side. It's really cool software that he's written for this. And it works also on the Raspberry Pi. So you just have to change. So I'm using NetBeans as my IDE. And this shows you how to set up a remote debugging platform in NetBeans. So I actually have this set up in my IDE, if you see. So I have a whole bunch of these set up, but when you add a new platform, just choose remote platform. And then you can enter in the information for your Raspberry Pi, which is hooked up via network to your computer. And it makes it very convenient because once you have the remote debugging set up, then you can actually, just from your computer, run things on the Raspberry Pi, and it will copy the jar file over and run it. It also lets you do profiling on the Raspberry Pi, so you can, easily run profilers to do performance testing. So this is the configuration for, the main class and the arguments and things. But the standard Java run dialog in NetBeans for setting up the platform works on the remote debugging platform. Here I've chosen my Raspberry Pi configuration. So that's great. And then now we can run real code on our little demo and actually get Super Mario working. There is one small problem, which is the default. Well, I'll let you guys guess. How fast do you think the HalfNes emulation is on the Raspberry Pi out of the box? Without any tuning. How many frames per second do you think you get? What? So we need 60 frames per second. On the original code base, we get 6. So not too good. Fortunately, we can improve the code base with some performance tuning. And so I've done some of this using the NetBeans profiler. And it's quite good because it shows you the runtime of different methods, and you can start figuring out where the hotspots are in your code. The other thing I was looking into was garbage collections to reduce the number of GCs happening, and also looking at method inlining. So you can get output from the compiler, the just-in-time compiler, on what it's inlining as it goes along to figure out which methods can't be optimized by the just-in-time compiler. So the Java implementation on the Raspberry Pi is quite good. It's the full Java SE implementation. It has a just-in-time compiler, so it's very performant. But you need to do a little bit of work compared to desktop because the processor is much slower. So here are some things which I made improvements in. Some of these worked and some didn't. So one thing I did is I changed the video from being based on Swing. The original code base used Swing as the graphics toolkit via X Windows, and I converted to use JavaFX instead. Has anyone here tried JavaFX? Nope. Yes, started. Yeah. So this is a huge performance improvement, especially on Raspberry Pi. So JavaFX has 3D graphics acceleration, and on the Raspberry Pi, it writes directly to the frame buffer. So it bypasses X windows, and it bypasses a bunch of layers, and it can write directly to the graphics subsystem. So it's much, much faster to do it via JavaFX rather than going through the Swing video. The second thing which I changed is there's synchronization between the three processors, as I mentioned. There's a CPU, a PPU, and an APU. To be 100% accurate, you need to do this pixel by pixel. However, Andrew had an older implementation of his code base, which did it by line, which is not as accurate. In particular, it breaks the Codemaster games. There's some games made by a UK company, but I don't care because I grew up in the US. So I went back to the implementation which does stuff per line because the Raspberry Pi is just not fast enough to do it per pixel. I also removed a bunch of bitwise helper functions. So when you're doing bit masks in Java, normally like the standard way to do it would be do and or big zero, well big longs specified as hexadecimal. And that gives you the best performance. He had some helper functions where you pass in the item and the mask or the bit he wanted to set or clear. And the helper function would go through and set or clear bits. But it was too slow because it couldn't inline it properly. So I wrote a regular expression which went through and replaced all the instances of his helper function with direct masks. And this actually was the biggest performance improvement of everything, just going through and getting rid of the helper functions for bit operations. He had a bunch of operations in the inner loops on the PPU. So that also caused some performance issues. So I moved those out to happen once per frame rather than once per line. The audio processing unit was using double math with longs, or was using double math rather than longs for the mathematics. On the Raspberry Pi, on a desktop it doesn't matter. On the Raspberry Pi, the floating point unit is not that fast. So by switching it over to longs, you get a lot more performance. In general, processors, while they're good at floating point math, it happens mostly serially. So you lose a lot of multi-threading performance whenever you use floating point graphics. So it's always something good to look at for your applications is if you're doing a lot of floating point calculations, like especially division, there's only one division processor in most processors, so you end up getting stuck on that. Array access via unsafe. So this one actually didn't help at all. Does anyone know what unsafe is? What? No. This has to do with there's a special package in the JDK called unsafe, and it lets you bypass memory protection and a whole bunch of other things. So for example, you can do direct memory access. So I was trying to avoid array bounds checks, right? So if you know the start position of the array and you do your own math, you can write and read directly to the array memory. It turns out that I did some tests with unsafe and without unsafe, and the performance was the same. So the compiler is optimized enough where it handles cases like this quite well. And in general, you really shouldn't use unsafe, because the reason the methods are called unsafe is because they're meant for the core JDK team to do their implementation. But at some point in the future, they're going to be removed. So if you create something which relies on it, at the best case is it'll break in the future and you'll have to rewrite it. The worst case is what you were trying to do won't be available in the future. This also didn't help much. There's an intrinsic for replacing loops with system array copy built into the JDK, so you don't need to do this optimization anymore. And there's also this last one, pulse width modulation audio. It's slightly hidden under the logo, but on the Raspberry Pi, audio was another big bottleneck, because whenever you flush the audio buffer, the audio is written via pulse width modulation. It's quite slow to do buffer flushes. So what I did is, rather than flushing once per frame, which is 60 frames per second, I flushed the audio buffer once every 3 or 4 frames. And that way, it causes a slight delay in the audio. So it's not perfect for like sound effects or certain things, because you get a slight lag. But I think if you were playing, you probably didn't notice too much difference, right? So, I mean, losing, you know, 2/60ths of a second isn't too bad for audio sound effects. So this is some of the performance things which I fixed.
I have one question.
Yeah, yeah.
So in the Raspberry Pi, I think that because of the hardware limitations, we are doing improvements in our code. So going forward, I think like earlier people who writes the C code.
Here, go ahead.
Yeah, the developers who write a C code, I think they actually care about each bit in a memory, and then they do a lot of improvements in their code. But in a Java, the developers, they don't care about all these kind of memory considerations and all. They just write a code and then develop it. Is going forward, because of the small Raspberry Pi kind of devices are coming up, do we need to consider all these kind of improvements at the code level?
Yeah, okay, so that's a good question. So I was specifically looking at things related to emulation performance. But even for like large enterprise applications, the same techniques I'm using, so like using profilers to profile your performance, looking at garbage collections and where things get inlined. Those are the same basic steps you go through to optimize an enterprise application. And you'd probably find different bottlenecks. Like for example, in like a server-side application, you'd be more likely to block on like network access. Or you might have multiple connections coming in and things are blocked maybe on database or some other constraint. But in high performance systems, you end up having some similar bottlenecks. So for example, one of the things which folks do with Java sometimes are high performance trading systems, where they care about extremely low latency. So they would actually care about doing optimization of some of this stuff for their application, because they have very high performance requirements.
So what about the mobile devices? So compared to Raspberry Pi, mobile devices have much better hardware, right? Or
Even for phones, you still have to worry quite a lot about performance. So they have faster processors on the Raspberry Pi, but it's the same type of processor. They're ARM processors. Similar type of GPUs inside of phones as well. And you're going to run into similar types of performance bottlenecks on mobile devices. Speaking of mobile devices, so have you guys heard of Gluon? Okay, so this is a company in Belgium, but they make a platform for writing applications in pure Java using JavaFX. So they actually built an application last year for Java 1. And it's written entirely in JavaFX. And it's a mobile application for Android and iOS. So I'll pass my phone around, but take a look at the application. I think it's a good example of what you can do with Java on phones and devices, and their platform is mostly open source, so you can download it and try it. They have the core platform is actually all OpenJDK and open source code, and it was originally developed by Oracle, but we contributed back to the OpenJDK project. They've picked it up and they're maintaining the open source JavaFX code base, and they've added some extra like cloud features and other platform features which you can also use, but those are the enterprise features. The core platform is free. But I would give it a try. I think it's a nice way for Java developers to get started with building. Yeah, so this runs on RoboVM. Yeah. Okay, so the way this technology works is it's a Java implementation on iOS and Android. For Android, it runs on top of the standard Android Java runtime. For iOS, since there's not a standard Java runtime, they cross-compile the code to native application using RoboVM.
I saw a long time back and I wanted to join the project, but time went.
But anyway, I mean, this it's a whole presentation itself, so we can do this in the future. Maybe next time I come, we'll do a presentation on this. But I think it's something interesting to try. It lets you easily build mobile applications in a pure Java solution.
Otherwise, we are end up with writing HTML code and then convert them HTML JavaScript and convert them into cross-platform and then deploying.
Yeah. No, I think this is a much nicer solution than doing a HTML5 based application because it feels more native, and it's pure Java code, so it's easier to work with. So you're writing the same code in the front end and the back end. It's a very nice solution. Okay, and last part is about 3D printing. So how many folks have a 3D printer? How many folks want a 3D printer? Okay, so that's good. So 3D printers have gotten quite affordable. You can build them yourself. There's more companies selling lower end 3D printer models which are quite affordable, and they all work on the same basic principle. You have a spool of plastic, and then you push this through a hot end at the other side, so it goes through an element which is heated to about 210 degrees Celsius, and that melts the plastic, and then you can draw in layers, and you build up the object in layers, and you can build very intricate structures. There's some types of objects you can only print on a 3D printer because of the layered construction, where typical manufacturing processes like injection molding, it's just not possible to make those sort of structures. So this is the printer I use, the Ultimaker, and the software I'm using is called Fusion 360 from Autodesk. This software it's a commercial package for doing 3D design, kind of like SolidWorks, which is the industry standard. But Autodesk is nice in that they provide a free student license, they provide a free hobbyist license, and a free startup license. So if you're not making money on your projects, if you're just doing it for hobby and interest, then you can apply for a free license and then use the software without paying. And then when you make money, if you have the startup or hobby license, when you actually have a big project and you're making your millions, then you can pay their license fee. Not a big deal. But the reason I use this software rather than like SketchUp or some of the other free packages is it's much easier to design something in this because you specify the exact dimensions. So you basically do a layout and you have precise dimensions, and then you tell it to maybe extrude to make a wall or to do different operations on the shapes. And then you can always go back and you can change previous dimensions and it'll recalculate the design. So that way, as you're prototyping, if you want to change the wall thickness or if you want to change the position of different components, it's much easier to go back and make modifications to your design.
So this entire case was printed using the 3D printer.
Yeah, so this case is 3D printed.
Okay.
So it's, entirely 3D printed, and it was also designed from scratch. So I did all of the case design using the software. This is the inside of the case. So it has some layers which hold the buttons in the center. The D-pad also is printed, and it all fits together like kind of like a puzzle. It's like a big jigsaw puzzle to fit the different pieces together, but it's designed so there's no mechanical parts. So everything is 3D printed. There's no screws. There's no hinge. The entire thing is designed so you just print it and then you snap it together and fit it so it works. Yeah, so I wasted time on small details, but the logo is also 3D printed. Even the text, like for the power button and all that stuff on the sides, that's all 3D printed. And it's not too hard, but like doing small details with the resolution of the 3D printer is sometimes hard. So for example, for the text, I printed a bunch of different text samples and had to adjust letter spacing to make it come out nice on the 3D printer. So the whole project for the modeling took about 2 weeks, but it was like 2 nonstop weeks. I was printing in the evening, and then during the day I was doing modeling, and I would, look at the prints at them in the morning to see what was working and what wasn't. I would change the design, and I would let the printer run overnight again to get a new print. And the reason it was compressed schedule like that was because I had 2 weeks left to finish the book. So this was one of the projects for my Raspberry Pi book, and it had to go to press, so I had to finish the project. So I had exactly 2 weeks. So I printed about exactly 12 versions of the full case, and then for smaller parts like the hinges, I printed it out in small versions so I could test things quicker rather than waiting for the whole case to print. So this is the hinge design. You can see I had lots of failures. There's a reason why people don't print hinges in plastic. My initial design for the hinge was to use a polyhedron, like a 20-sided polyhedron, and that way it would snap at fixed positions. But so when you use a sharp edges like that and you open and close it, it takes about 50 times and it's perfectly smooth, like you printed a circle. So that doesn't work very well, sharp edges. So it's quite a hard challenge to do design like this.
How much it cost for you printing the case?
Oh, the material cost for printing the case?
Yeah.
Let me think. I think this whole case takes about maybe a fifth of a spool, and the spools are about $30, so maybe $6 to print a case. You can get cheaper materials, so maybe you could print it for like $4. But really, this type of manufacturing is designed. What?
That kind of case manufacturers are not available, so you printed on your own.
Yeah. So this is best for things which you're prototyping during the design phase. Once you've finished and it's like ready for production, if you want to print thousands of these, what you would do is you would give this to a company which would make a mold out of it. They'd turn it into an injection mold, And then once you, the injection mold itself is going to cost a few $1,000s to build a proper mold. But then once you do that, you can quickly manufacture for pennies a lot of units. 3D printers are best for prototyping though, because you wouldn't pay the cost of building an injection mold just for one trial. So for the hinge, the design I ended up for the actual hinge is it's 2 triangles inside the hinge, and they're connected at the center. And one of the triangles is slightly larger than the other. So they're slightly different sizes. Okay. So the way this works is it produces a shape which is it's like a slightly oblong triangle, kind of like that. And when you try to rotate a shape like this, it's only happy every 120 degrees. And in the middle, when it's 60 degrees off, it has a little bit of friction. So you can feel that in the hinge, right? So it stays open. When you start closing it, it has resistance. And then this is the stiffest position when it's exactly 60 degrees off. And then when it closes, it stays shut. So this works better for plastic material, a design like this, because what it's doing is it's rather than having a hard edge, which will rub off eventually, it stretches the plastic when it moves, right? It's going to make the hinge material stretch slightly to accommodate the motion. And plastic is a fairly flexible material, so it'll return back to the original shape. And this hinge design was somewhat inspired by my daughter. I was watching her play with her Nintendo DS, and I noticed well, they use metal hinges on the Nintendo DSs, but I noticed they only stay open at this angle. It doesn't lock at other positions. So rather than trying to create a hinge which would stop at arbitrary points, I just decided it only needs to be 120 degrees and 0 degrees, and that's an easier design constraint. Yeah, okay. So question is whether it auto powers off when you close the door. So that's a good feature. If you want to help me implement a little switch, so when you close it, there's a limit switch and it'll flip off the screen, that would be good. Good for saving power. Sleep mode? Yeah, yeah. Well, I mean, just powering off the LCD would actually save quite a lot of power. This shows the interference diagram of the hinge. So they have a special mode in Fusion 360 where you can see overlap. And this is when it's partially closed, so 60 degrees off, and it's exactly 28.254 cubic millimeters of overlap of material. And I tweaked this back and forth and tried different combinations, but this seemed about right for my printer and how it came out. But I've published all the models for this, so if you were printing it yourself, you could also modify the parameters slightly to change the amount of overlap. And this shows the slicing software, Kippah, which is an open source software for converting the 3D designs into printer instructions. So if you had a printer, you'd be using either Slicer or Kippah or one of these packages to then convert it into something you could print. This shows the actual printer printing the base layer by layer. So it's not quite done, but you can see it's building it up layer by layer. The whole design of this case is it's designed so you don't need any support material to print it. So everything's designed so when you're printing, there's something below it that you can build layers on top of. If you print in the air, you get a big mess because there's nothing to support the material. Some cases are okay though, like you see in the back here, those openings, it prints across, it does what's called bridging to go across that. It's not perfect, so if you look at the case, you can see the top edge is not as clean as the bottom edge if you look very carefully at the detail. But it's good enough, right? It's not too bad. if you keep the gap not too wide when you're doing bridging like this. There's little things about the constraints of the printer which you're trying to print, which are interesting. This shows the materials on the top. Pass it around again. And if you guys want, you can pick a game to play. You can change. You don't have to play Mario. You can change the game. This shows the little pins. So like I mentioned, I designed this so it's all snaps together. There's no screws or things holding it together, which I think it makes the design a little bit harder. But when you have a project like this on Thingiverse or you're asking other people to try it, if you tell them you need to print this and you need to buy a like 0.2 millimeter special threaded with this type of end cap on its screw, they're never going to find the right part, and therefore they won't try the project. I find it frustrating when I go online and I try to print things, and the bill of materials is very complicated where you can't get the parts you need. So I tried to 3D print everything so that it doesn't require any special parts like that. So this is the whole set of parts. The base, this is the cover, this is the top screen, some pins to hold it together, the D-pad, and then these two are layers which go in the center to hold the buttons. So I didn't use a PCB, because again, like if I ask people to print a special circuit board for the design, it's probably better, but then a lot of people are going to be turned away by the extra cost and hassle. So I think this is easier. It doesn't have a circuit board, but I 3D printed some button holders which keep everything nicely in place. Here are the buttons. I just fan out the legs to make it fit a little bit flatter inside the case for space. And soldering to the buttons directly. So this way, since you're directly soldering connections, you don't need a circuit board inside of it. This is the base with the Raspberry Pi inserted. It has a little slot which holds it securely in place. It has a battery. I think it's a 4,000 milliamp battery I put in here. My daughter's requirement was that this should last a car ride. So my first battery only had like 2 hours, which is not good enough. So this one will last about six and a half hours of playtime. So it's quite good for, long trips, playing on the airplane. There's a little circuit board in the back here from Adafruit called the Power Boost. And I would recommend if you're doing a small project with a battery to use a board like this, because it provides the charge port on the side, so you can charge it using a normal micro USB. And it also powers the Raspberry Pi off the micro USB, so you can play without the battery. It also charges the Pi off this, and it has lights for like low battery, charging, all of the standard indications you have on a phone. The chip on this board is the same chip used in a lot of Android phones for the power circuitry for charging. So it's quite good. And I made sure the LEDs are facing outside, and I made little cutouts on the back of the Raspberry Pi so that you can kind of see the different indicator lights for charging and different stuff. So here's everything with the Kippah installed to the LCD screen now. Some button holders added. So there's two parts. One holds the D-pad, and the other one holds the rest of the buttons and the speaker. There's a small speaker and amplifier board inside. This is also from Adafruit, and that's how you get, sound. And then this is the touch screen, which connects on the top. And I made these holes very big so that it's easy to get the ribbon cable through. So you can wrap the ribbon cable and then go up to the screen. Although I probably need a slight redesign, because as you see, the cover is broken. So my daughter was playing with it, and come on in. No? So the cover here got caught on the hinge, and then she forced it, and it snapped. So I probably need to put a little lip on it so it stays in place underneath the hinge opening and closing. So maybe the next version I'll tweak that slightly. This is the daughter board. And then this hooks up to the LCD screen on top here. And like I said, everything is designed so it snaps together. So there's a pin in the side, so you put these in the side, and there's a little hole you can see right here. This is the other side. You can see the hole more clearly here. And that hole has a slot in it, so from the top you can put down these little locking pins on either side, and then the screen goes on top of this and actually locks it in place. And the same thing, like for the screen, there's two areas you need support material, here and here. It prints without this, but I found it prints more reliably with a little bit of support material. So I built it into the model with the support material, and you just break it off with your fingers or pliers when you're done printing. And the screen in the whole case is designed so it all slides together nicely. So like there's pins on the top and little channels on the side. So you slide it down from the top, and then you just pop it out a little bit and you push it in here. So by having two directions, by going down and then having pins which go the other direction, it locks it in place securely without the need for screws. So you can pry it open with your fingers. It's not too tight, but it's also stays pretty sturdy, right? We were passing it around and using it, and this particular console's made it all around the world. So it's withheld quite a lot of abuse. Okay, and then here's the finished console. This was the first night we got it done, so the first one was red in color. And this is my daughter testing Mario, where she got quite upset at beating the first stage and then be given a horrible message. But you know, it's good to have kids who can test it. All right, and we have one last video clip for you guys. So anybody ever play Metroid? Okay, so this game was one of the early non-linear platform games, and if you got the good ending, if you actually got all of the items in the game, then you found out that the character which you've been playing with for the whole game, you know, you're in a spacesuit, so you can't see your character, but it's actually a female character. So later Nintendo games, they give you the option, like in Super Smash Brothers, you can play like Zero Suit Samus or regular Samus, but this is one of the earliest, you know, popular video games with a female main character. So I think we need more female programmers. I do a lot of kids workshops, and it's a very good ratio in the kids workshops of girls to boys. But you can see, like us adults, heavily biased towards male programmers, and I think it's something perception-wise it's good to change in the industry. The game? The software, it's just Java code running on the Raspberry Pi. There's the standard Raspberry Pi distribution comes with a Java SE runtime. And like I showed you in NetBeans, you just configure it as a remote platform, and you can run your code on the Raspberry Pi. So it's very easy to do.
Does it have any kind of JDK or something? Because on our system we have our executables.
Here, let me give you the mic.
My question is, on a computer we have all those runnable environments for running a Java program like JDK, JRE and all. So does it have any kind of such environments?
Yeah, so the default Raspberry Pi distribution is called Raspbian. It's a variant of Debian, and it's a Linux-based operating system. And the standard Raspbian distribution comes with a Java runtime. It's a full Java SE runtime with the JDK. So you can compile on it. You can run jar applications on it. It has JavaFX support, so it's, you know, a full-featured runtime.
Okay. So it captures the program will capture all your buttons, right? Or the button movements and all.
So I modified the HalfNes code base to support GPIO. So it's using a library called Py4j for the GPIO support, and it's capturing all of the inputs.
Okay.
And then it's treating that as a controller.
Okay.
And also, I have support for USB controllers too. You can hook up a external USB controller and then play with a standard gamepad.
Okay.
Okay, so this is the the Thingiverse project, which has all the details in it. So you can go here and you can print it or see the hardware list. This also is one of the projects from the book I just wrote, Raspberry Pi with Java, Programming the Internet of Things. So this book covers a whole bunch of different Java topics. It covers how to get set up with Java on Raspberry Pi. Has some simpler projects, so it has a coffee demo, a line following robot, a magic hat which uses an RFID sensor so that you can read the card while you can cheat. And the RetroPi is also in here. There's also a drone and some other projects, so it's a lot of fun. It's basically like it's a technical reference, but it's also written in a project style, so you can have different projects to try out. So hopefully, you guys learned a little bit from this project, and my description of how it was done. I think it was a lot of fun to do, and I would strongly recommend getting a Raspberry Pi if you don't have one. There's lots of good online references, and I also recently wrote a book on this, and I think it's fun to find things in your life where you can build projects and hack and do things which interface with the real world, rather than just it being pure server-side programming for your Java day-to-day work. Yeah, so I did garbage collection profiling on the code base, and it turns out that the way he wrote the code base, there's very little garbage produced during normal runtime. But when you first start it, I don't know if you noticed this when you first started playing Mario. At the beginning, it's a little bit chunky, and then as the just-in-time compiler warms up, it gets faster. So the initial performance is slower because of the garbage collection, and it hasn't JITted everything yet. And once it reaches a steady state, there's not a lot of garbage being produced. Most of the emulator basically operates on these huge arrays of memory, which is the ROMs. So there's very little new objects being created during normal runtime. Okay, so thank you guys very much. And I'll turn it back over to you. You want the